So if we are here, we have a combination of some amount of ferrite and some amount of this weird compound, which I'm not going to get into a crystal structure here because it's too complicated, right? A mixture of these two. If I'm in all this area here, can anybody tell me how can I know how much ferrite and how much cementite I would have if I had to calculate it for a given alloy? Lever rule, right? Who said that? Okay, thank you. Right, that's the way we go. So for normal steels, what should we have? Lots of ferrite or lots of cementite? Lots of ferrite, right? The closer I'm to here, that means the more I have of this phase. All right, so here I have this mixture of ferrite and cementite. Here I have pure austenite. What do I have here? What do I have? Ferrite and austenite, right? And we would calculate how much of each that way. So I think here I have some microstructures of what would look like the microstructure of a steel at different temperatures, right? Here we're in pure austenite, so the steel would look something like this, right? These are the grains of austenite at high temperatures, the FCC. If we're here, and the name for here is the intercritical region, at least in welding, that's what we call it. In the intercritical region, you would see some amounts of ferrite and some amounts of austenite. In this case, it looks all kind of weird here. That used to be austenite, and now it became something else, which we are going to discuss, right? A mixture of the two. And then when we are in 3, right, we have a mixture of ferrite and perlite here. It's a funny thing that when we said there is some ferrite and some cementite, but the cementite doesn't come alone. Typically comes by through this point, the eutectoid point, right? As this perlite here. You see that looks like a fingerprint, right? The fingerprints are layers of ferrite and cementite, right? And so we have the primary ferrite that would come from going through the intercritical region, and then the austenite we had left turns into perlite, as you get to see here. Okay? So I assume it's okay with Maris, like the Mekis. How are we doing? More or less? You have other Mekis we have. You saw this in Mari 202, right? And you went over this. So it might need a little bit of a refresher by the time you get to the exam. But okay, what I explained to you in 5 minutes is the effect of temperature and the effect of composition, right? That's essentially thermodynamics. But the fun starts when we talk about time, because when we have transformations, for example, from austenite to ferrite, right? As we cool down, we go from the FCC to the BCC. The atoms need to rearrange. Well, it doesn't happen instantly. Well, it can happen instantly, right? But they want to find new places. Something even more interesting in when you have a normal steel, and it is that, remember I mentioned ferrite can take precious little carbon. Here, this is about as much carbon as you can take in the ferrite, right? So you have a bunch of austenite in a normal steel at 0.2%, right? That is about here. This is about 0.02. See, if we are at 0.2%, what happens with that carbon that was in the austenite, right? I start to having ferrite that has this BCC structure, but this ferrite has to spit out the carbon, right? And has to form the cementite, right? So there are chemical reactions, the formation of cementite, there are diffusion, the carbon needs to get out of the crystalline structure of ferrite, right? And so this is what is called carbon partition, right? And this carbon partition, right, is a diffusional process and takes time. And because it's diffusional, you can imagine if it is hotter, diffuses faster. You know this intuitively, right? But there are all these type of formulas. If it is longer distances, it's going to take longer, right? All those type of things. So there is also another thing is if I'm really at the line between partitioning and not partitioning, my partitioning is going to be relatively slow. In materials engineering, we say the driving force is small. Now, if I should have partitioned, but I'm much colder than that, right? Now I'm saying, wow, I should have been all partitioned, but I'm not partitioned yet. So my driving force is huge, right? So we have these two effects for the phase transformations. One is temperature. High temperatures make things move fast. And the other is driving force, in which the more what is called undercooling, the farther away, the colder I am from where I would have partitioned, means I have a bigger driving force. And we're going to see how those two things compete. So I'm going to suggest, right, this is an introduction of run-of-the-mill metallurgy, but I want to use this for understanding welding. So I'm going to suggest one experiment, right? A very easy experiment that is, let's do it in our minds, although we can do it in the equipment in the lab. Let's heat a piece of a steel of this composition. It's 0.77%, right? And I chose this conveniently for a good reason. And let's say I heat it up to the 0.1. In 0.1, what should I have? What should the crystal structure be? FCC, austenite, right? Should I have carbides in this case? I shouldn't, right? All the carbon is in solution inside the austenite. By the way, that's very common in most steels, even when you have alloying elements. Okay. We stay here for a while, right? And we make sure everything is homogeneous. And then we cool down to 0.2, right? This is not room temperature. I'm saying we cool it down to something that is like 550 degrees or 600, something like that, this steel. What should I have here? What does this diagram tell me I should have? A pure perlite, right? Some combination of ferrite and cementite, but because it's right here, this is perlite. So the whole microstructure here should look like all fingerprints, right? No primary ferrite, no, just fingerprints. Very easy. And there is no intercritical region here. It just goes from one to the other, right? This is a very easy transformation. By the way, you seldom want to weld this type of steels. We might be getting a project in which we do it, but they're not the easiest one to weld. Okay, so if we go, boom, from 1 to 2, right? And we hold it here at this temperature, typically in a salt bath or something, right? Because this is fairly hot. This would be kind of borderline red hot, right? This should be pure perlite. And let's do it. So if we go from 1 to 2, what we're going to see is that from the pure austenite, it doesn't turn into perlite instantly. It takes some time, right? And it goes. It takes a while to grow. If this is a moment of quenching, very little transforms until it kind of woof, starts transforming fast. And then when it reaches 100% transformation, slows down again. Right? Can you imagine this? I mean, all this, we can do experiments. The problem is, it would be a whole year of a materials curriculum. So I'm banking a part on what you already know and part on what you can imagine. So let's say that we pick like 1% or some arbitrary number to say, OK, we start transforming here, right? It took some time to start transforming. In reality, it starts transforming at time 0. But you don't notice. You don't see it. But say like 1%. And then it transforms, and let's say it finishes. And again, it never finishes because it's asymptotic. But let's say when you reach 95, 99%, some kind of arbitrary number, we call it finish, right? So based on this thought exercise that I suggested, we can define a start and a finish of the transformation. And we know this time is related to the temperature, to the driving force, right? Okay. And so now let's do the same experiment not only for 2, but for 3 and 4. So we are defining a start and a stop, right? What do you think, if I go really close to this line, do you think the start would be faster or slower? If I'm really close to this line. Okay, I like that. Why slower?
Because the temperature gradient is small.
Let's say there's no temperature gradient, that everything is isothermal. But I think I know what you want to say, but gradient is not the word. See? Then they're cooling, right? The driving force is very small, right? If I'm right under this line, if I'm just above the line, I will never transform. If I'm on the line, the atoms are like, maybe yes, maybe not. If I'm right below the line, yeah, I should go, but I don't have so much motivation, right? If I were to be much colder than number 2, let's say 4, right? Would it be faster or slower? Slower again or faster? Slower, okay. So I'm slower no matter what I do, okay. But I'm going with that. Why would it be slower? Right, if it is colder, diffusion is very sluggish. My driving force is huge. Now I'm really motivated. But the couch is made out of Velcro, so I just cannot get out of it. So here, I'm not that motivated. Okay, so we talked about the starts, and we thought together, and we agreed on something. And of course, the story is very similar for the finish of the transformation. So I could make a graph with the start transformation and the finish transformation, right? And this is something you're quite familiar with, right? And in this graph, we have different temperatures, all for the same experiment, which is funny enough, it's an experiment that people did only late in the understanding of steels. This experiment of saying, let's heat it up, cool it down fast to a certain temperature and hold, that's quite a contrived experiment. There's pretty much no real process that is like that. But it's good to understand. So I'm telling you first the crazy experiment because it's the easiest one to explain. But once I explain the weird experiment, we'll talk about the reality of welding, and it should resonate with you. So what is this curve that says, well, if we go from austenite to 800, or from austenite to 600, or austenite to 400, this experiment I mentioned, and you hold, this, the horizontal axis is time. This would be my start time. This would be my finish time, right? And this is in log scale. So you realize that this is 10 times lower than this, and this 10 times lower than this, right? It's quite significant. And what we see in this curve, some people call it a C curve, right, is that if I'm close, this is the eutectoid temperature, right, the 727, right? And I pick this steel that nobody wants to weld, right? I'm telling you, crazy experiment on a crazy material. But the explanation is the easiest, right? So if I'm above here, nothing is ever going to happen. If I'm just below, it's going to take very, very long, right? And as I get down to it, right combination of driving force and diffusion, it can be very fast. And then it starts to get slower, slower, slower again, right? One important thing to know, we can prove this, but just take my word for now. When your transformations happen at high temperatures, they tend to have coarse features. And when the transformations happen at lower temperatures, they tend to have fine features. Right? This is related with the driving force and surface energy. But for now, let's keep in mind this thing. High temperatures, coarse features, lower temperatures, fine features. Now, this curve has a funny business down here, which some of you might know what that is. And it's when some things that are not in the phase diagram. So what happens, now, if we do the same experiment, we austenize, right? We're in austenite. We solutionize all the carbides. Is all the carbon in solution in the austenite, and I quench in a bucket of water, right? Like the swords in the movies, like I quench my red hot sword in a bucket of water, right? So what happens then? Martensite, right? And what happens is that now I'm not giving the carbon a chance to partition. Not a chance. Not a chance. There's not enough time. And the carbon cannot get out because it's too cold. And now the BCC that cannot take any carbon is stuck with the carbon, right? And then in the case of these martensites with relatively high carbon, you turn into a BCT, right? It's not BCC anymore, it's a BCT, body center tetragonal. So the carbon happens like by distorting the lattice, right? And martensite is very hard, it's very brittle, right? Has all the carbides in solution. And there's a temperature at which that can happen, right? And this is the MS. MS is a temperature at which martensite starts. And then as you cool down, you would go to 50% martensite or 90% martensite. What do you call what has not transformed into martensite? Do you remember? Word everybody? Austenite. Retained austenite, right? That's the famous retained austenite. And what happens is as the martensite is forming, is distorting the lattice, introducing lots of strain energy, right? Such that it gets to a point in which the austenite cannot transform anymore because it's transforming into, it would require too much strain energy to transform. So that austenite is retained because of this strong strain energy, right? This is the martensite, right? Martensite is hard, brittle. It would give us problems of hydrogen cracking. Okay, I want to tell you about one more thing. Imagine I do this same experiment as always, and I stop right before forming martensite, right? So I would have austenite here, and I hold it, right? And then the carbon partition happens in a weird way. Happens in a hybrid mechanism in which you have some amount of, something I forgot to tell you. In martensite, the atoms rearrange in a way that is called military, like all shear and form at the same time. They don't diffuse, right? Because you don't diffuse, it can be fast. All the other things, carbon partition involve diffusion. Now, if you go down here, the partition would be a mixture of would involve diffusion, but would be a displacive element to it, like some elements of martensite, of the atoms trying to rearrange military. So, what is bainite? Well, people have gone into incredible arguments about what bainite is, so I'm not going to get there. But I can tell you something. In bainite, you have diffusion, and you also have displacement. So bainite is some kind of combination of what we know of martensite and what we know of all the other transformations in which the carbon is diffusing, right? Now, the diagrams you're going to see, you see that says P, that's for perlite. B, bainite, right? Here is for austenite. All this is austenite, right? And here it says austenite plus perlite forming, austenite plus bainite. M is for martensite. This bainite here, when we talk about welding, has a lot of different shapes, right? So when a metallurgy talks about bainite, they tend to talk upper bainite, lower bainite in a somewhat abstract sense. In welding, these bainitic transformations, this hybrid of displacive, like martensite-like shear and diffusion, they have many different aspects. All right. So let's talk now about something closer to home, right? A 1040 steel. Again, you seldom want to weld steels that have 0.4% carbon, right? They can form martensite, they can crack. You need to preheat, lots of things. So this is a more reasonable steel to talk about, but there will be different features. So I want to discuss the same crazy heat treatment of holding to austenite, then quenching, holding it in a salt bath at different temperatures, right? You'll never do that. Crazy experiment, but I say an experiment that helps us think and understand, right? But let's do it not with a eutectoid steel, not with a 1080 steel, but with a 1040 steel. That is commonly available, often welded. So here in equilibrium, we should have like ferrite and perlite, right? Mixture of ferrite and cementite, which in reality is primary ferrite, right? And then the perlite that comes from here, right? For the mechis, I think this is important, but I cannot slow down too much. But if you go back to your notes on MATI 202, it's all in there, and if not, let's talk, right? This is not too deep. You should feel comfortable with this. All right, so let's go from austenite and quench at different, and let's see different things. For example, if I quench to 800 degrees, right? 800 degrees. I'm right above the line that tells me this is all austenite, right? So nothing is going to transform, right? So, and there is another thing I forgot to tell you. This line here is what people call A3. Why? I don't know. I suspect A is for austenite. Why is 3? I don't know. And this other line down here, right? And there is the A1, right? The temperature at which A1 is when during heating you would start generating austenite. A3 is when during heating you would finish generating austenite, right? So here we have, or here they put it as A start and A finish, but nobody does that. This would be A1 and A3. So if I'm above A3, nothing is going to happen because it's all austenite. So if I go to and hold to 700 C, right? 700 C is here in the intercritical region, right? So in the intercritical region, 700 C means the austenite will start precipitating some primary ferrite, right? Some primary ferrite, and then I'm going to have this combination of the austenite and primary ferrite. Forever, it's living in a salt bath, right? Austenite plus primary ferrite. This is a primary ferrite, these things here. And who would remember where the primary ferrite tends to nucleate? Grain boundary, yeah, the standard answer, right? Yeah, that's where the primary ferrite typically nucleates. So let's say now we go from 800 to 600. Right? 600 C. And what happens? Well, I go from austenite, I start to have some primary ferrite, and then I start to generate some perlite, right? And when you see these type of diagrams, this is, in this case, is a TTT diagram. Everybody gives them different names. Remember, I just showed you that said P for perlite, but perlite is ferrite plus cementite, right? In this other diagram, people call it AFC, austenite, ferrite, and cementite. But we know it's perlite. You have to know, right? People don't mean to throw you off, but you can be totally thrown off until you get a hold of these, right? So sometimes they say P, perlite, sure. And sometimes they say F and C, perlite. And this stands also for the primary ferrite. Okay. And it says here that at about 1 second, I would start generating primary ferrite. At about 10 seconds, I would start generating perlite. And at about, what is this? 200, 200, 300, at about 300, at about 400 seconds, right? I would stop generating the perlite, and I'm done. If I'm here, right, at this temperature, and then I quench in a bucket of water, what would happen? Would I have phase transformations? Would I get martensite? No. No, because all the austenite got consumed, right? Austenite is the fuel for the phase transformations. So if I use all my fuel into generating my primary ferrite and my perlite, I run out of things. I can quench it and rock and roll. Nothing changes. Okay. Let's quench to 450 degrees. 450 degrees, where are we? 450 here, right? And in this case, what the diagram says that about, what is that? We start transforming into bainite. You see, we're in the lower part. At about 1 second, after about 150 seconds, we finish transforming to bainite. According to this diagram, if I hold at 450 degrees, am I going to have primary ferrite? No. No, right? This diagram says if I hold on to here, I go straight into bainite. Straight into bainite. You see that the back has like this kind of squiggly line. This is perlite, and this is the bainite nose. Right? So they put F plus C because that's what bainite is, and that's what perlite is. Ferrite and carbides. They're not trying to throw us off, but nobody would say that this here, this on top is the same as here, this in the bottom. This is perlite and this is bainite. Quite different things. Quite different because in bainite is quite tough and hard. Perlite, not so much. All right. And then if we quench all the way to room temperature and hold, what are we going to have? Right, according to this. Room temperature is, what did I put? Room temperature? Well, room temperature would be way down there, right? So, down here, that would be martensite, right? And depending how deep we go, we can have 50% martensite, 90% martensite, and keeps going, right? Something I didn't point out, you see in this one, the lower the temperature, the finer the features, and the harder it is. So if we go back to where we started, by reading the diagram, it gives us here what hardness they predict. We would predict 23 Rockwell. Right? 23 Rockwell if we hold at high temperatures, 30 Rockwell at lower temperatures, 61 Rockwell if we go to martensite. So the lower they hold. But this is all theory. Still, I want to tell you one more thing about theory. Something called hardenability. And it's an interesting concept. So martensite is hard, right? So, but to get martensite, I needed to cool very quickly, because if I don't cool quickly enough, it's going to start transforming on me, right? So imagine now I want to make a huge shaft, right? This is an old problem of like people doing big equipment like shaft for ships. You want it to be hard with martensite. And you quench it, but you quench the surface. The inside takes forever to cool down, right? that's never going to be too hard. So people figured out that if you put alloying elements, right, you can slow the decomposition of the austenite such that you can reach austenite at low temperatures and then it turns into martensite, right? Then these steels are called hardenable. That doesn't mean that you're harder. It means they can reach martensite even at slower cooling rates, right? So how do you get this hardenability? Well, you can do two things. One is to put things that involve the diffusion not only of carbon. Carbon is what we call an interstitial. It goes inside the lattice. But you can have substitutional elements. And the substitutional elements then need to diffuse, right? But they're much lower. So as you delay now this partition, the steel can reach austenite, can reach martensite. Another thing you can do is to play games with the driving forces, right, and make the austenite more or less stable. So this is good for heat treatment, and people design steels like 4340 to be very heat treatable. Now, for welders, that's horrible, because that means the unintentional heat treatment of welding is going to end up being super hard with all the possibilities of hydrogen cracking, low toughness, brittleness. So I put this list here not for you to memorize, but to see some things, how some elements stabilize the austenite, how some elements stabilize the ferrite. For example, take a look at this. Austenitic stainless steels, right? Austenitic stainless steels, as you can imagine, they want to be in austenite. And what do they have? Lots of nickel, right? But if you don't put too much nickel, you see chromium here that makes it stainless is a promoter of the ferrite, right? So right there you start to see how some chemical elements like nickel or chromium, like chromium, which is there to make the steel stainless, it needs to be counterbalanced with lots of nickel to be austenitic. All right, so look at this. Here's the effect of alloying. This diagram we already studied it in detail, right? And this is the 1040 steel. Let's forget about the 1% manganese, which actually has a significant effect. And we saw how we can get the primary ferrite and perlite or bainite without any primary ferrite. We saw that, how we could get martensite. We saw all those things. And we saw the times. For example, it would take, if I'm any slower than 1 second, I would start like partitioning. I would start like transforming my austenite. Now, here we have a steel, right, that has a whole lot of alloying components, right? And but it's 0.4 carbon, 1% manganese, same as before, but has some chromium and moly and nickel. Look, any decomposition doesn't start until 10 seconds, give or take. This is very hardenable. This is going to be a nightmare to weld, because that means no matter how I weld, it's going to end up being martensite, because the weld cools down typically in less than 10 seconds, right? So you get to see the effect. And the diagrams, look at the similarities. They look different, but look, primary ferrite here, primary ferrite here. A nose for the pearlitic transformation, a nose for pearlitic transformation. A nose for the bainitic transformation, a nose for the bainitic transformation. The MS, M50, M90 here. Look at the hardness. They are not that different, the hardnesses of these steels, right? If we were to do a holding heat treatment, they would end up with very comparable hardnesses. This steel here is not harder than this steel here. Now, if I cool down this steel in 10 seconds, I'm going to have all martensite. If I cool down this steel in 10 seconds, I'm going to have all kind of decomposition products of austenite, right? Okay, so none of this is good for welding. But what is good for welding? Well, in welding, we have a constant cooling rate, right? The constant cooling. But the experiments I was telling you, they didn't account for cooling. Said you hold in austenite, then you quench, and you hold, right? You quench in a salt bath, so you hold it at 600 or you hold it at 450. Nobody does that. You will not do that. But it gave me a way of explaining things to you that seem relatively easy. If it didn't seem easy, it can be so much more complex. The reality of welding, and that's the way metallurgy is starting doing things, doing this continuous cooling. But, right, this diagram is not good for that. Can anybody tell me why I made the cooling as a bent line, if it is a constant cooling rate?
Because it's a
Log scale, right? Log scale here. So this is constant cooling rate, right? It's not an accelerating cooling rate, right? Okay. What do? You do a diagram in which it's very similar, right? Like you could do like some sort of integral of small increments, right? But in reality, you just do another experiment. We have the thing to do the experiment is a dilatometer, right? And then you get this other diagram, right? This is the CCT diagram, right? Continuous cooling and transformation diagram. The CCT, and this is the TTT diagram, right? This is a time and temperature transformation diagram that is isothermal holds. These two diagrams are very similar. Look, vertical axis means temperature in both. Horizontal axis is time in log scale in both. What we see here is what phases we're going to have. But in this case of the CCT diagram, is you read it as following the, something moved in there, that's ugly. This should have been on top of something. Okay, you follow the lines as they cool, right? So at the beginning you have austenite, right, just as before, and then you would have this F. What do you think this F stands for? What ferrite? Primary ferrite. Proeutectoid, yes, that's another proper term, right? This is what it says here. Here it says A plus F. Here it says only F. What is A plus F here? Austenite plus ferrite. Why do you think I have austenite here or not? Yes, I have austenite. And again, they don't mean to throw you off, but they do a pretty good job at it, though, right? Like, so they take for granted you would know that if you have perlite here, you had some austenite in here. Actually, look at this. This is a pretty awesome diagram. See, it says 50 here. It says 50% ferrite. The other 50% being austenite, right? And imagine I was holding here. Here I would have perlite, right? And here it says, now I have the other 50% of perlite. Right? These diagrams are very important because these diagrams are important for welding. This diagram is super important for welding. But just as a refresher, I wanted to make sure we were all on the same page. So let's pick this other line. Well, we're going to do it later. But you see ferrite, perlite. Here we have bainite. Here we have martensite. Right? Same things as before. But the diagram is not the same because now life is a lot more difficult. As we cool down, we have a constantly changing driving forces, constantly changing kinetics. And you can start with some coarse features happening at high temperatures, followed by a mixture of other features that happen at lower temperatures. Very, very different thing. But the concepts are similar. And here we have often depends on the CCT diagram, we would have the Vickers hardness or the Rockwell hardness. And these numbers here are the cooling rate, in this case in Fahrenheit per minute. How useful, right? But again, but this is cooling rate. Slow cooling rates, fast cooling rates. All right, so these two diagrams, very similar. Yet, from a quantitative point of view, the CCT is much more relevant to welding, right? And even then, the CCTs have like little tricks in welding, right? Because the CCT depends on the austenite grain size. And in the weld, the austenite grain size changes all over the place in the heat-affected zone. I'm going to discuss this in a minute, right? But this CCT diagram is what matters for welding. So let's look at 1040 steel. This is the same steel we have been looking at for the TTTs, right? And this would be a cooling curve for 1040. Would you say that this is constant cooling? What do you call when the line goes up? When you call that heating? So what's going on? So this is something super interesting. I had a student actually get a master's, another get a PhD on these type of things. When this is austenite here, and here it started to transform in whatever it is, right? So you have an enthalpy associated with the transformation. When you transform, for example, when you go from liquid to solid, it releases heat, right? And when it releases heat, it sees this bump from the internal heating. So these curves are experimental curves. Of course they meant, and with modern equipment, you typically can do a better job. But if you start going too fast, you start to see this effect is called recalescence. So let's forget this bump here, which is so important that you can even get a PhD. Let's forget it and claim it in reality goes all down straight. And let's determine for this steel the final microstructure and the final hardness. Can anybody tell me what the final microstructure for this is? You're going to do it in an exam, but right now it's just nothing but friendly. Okay, how much? 6% bainite. What else? 85%. No, I don't agree. Well, okay, what do you mean by ferrite? Well, the final microstructure will have close to very little austenite. I would start looking from up here. This is 100% austenite. What do I have here? Yeah, 92% austenite plus 8% primary ferrite. Where does it nucleate? Grain boundaries, right? Like you start having a microstructure in your mind. You can even make a drawing. Then you keep cooling. Let's forget this hump there. But this hump came from this, the nucleation of this primary ferrite. So it comes down, and then what do I have here? So I have 8% ferrite plus 85% perlite plus remainder of austenite, which is my fuel. That's still fuel. So how much?
No, and then changes, right?
Right, and then it changes here, right? And it gives me 6% of bainite. This is a perlite. So if I do 8 and 85 and 6, how much does it add up to? 99. So I have 1% of austenite. No, the 6% transformed to martensite as it crosses these lines, right? So now, this is a lot more complex than these Mickey Mouse TTT diagrams I was showing you that nobody does, but it gave me a chance to explain to you. Now you got the works, you got everything. You got bainite and perlite and primary ferrite and martensite, right? And actually, it doesn't say here, but not all once you start transforming martensite, not all of it goes. You have some amount of retained austenite too, right? So you have the works, right? Here you go. Oh, there you go. This is what we were talking about. Oh, and the final hardness is indicated here. 287 Vickers, or 28 Rockwell C, right? So if you wanted something softer, what can you do? Let's say that your weld has a code, and typically the code will tell you that you want to be below 28, right? What would you do? Say, cool slower, right? So if you cool slower, the hardness starts to go down. But all of a sudden you realize that I'm going to be teaching you, but some of these cooling rates are really slow. So if it is a little bit slower, well, you can increase the heat input, as we already discussed intuitively. More heat input gives me a slower weld, right? And we already discussed intuitively how it's going to be softer. Now you would know exactly how much softer. You can use a preheat, because the speed of cooling is given by the difference between the temperature of the weld and the temperature of the plate. If the plate is already pre-hot, it kind of tempers a little bit, yeah.
What would be different? What would be better, or what would be the difference between having a preheating process or cooling down and then go up a little bit, like with a torch or something? Like,
okay, this is what people would call, for example, post-weld heat treatment, right? So the difference is actually huge, because if you can increase your heat input and you're good, that costs you no money. If you need to do a post-weld heat treatment, you need to take your whole part to a heat treatment furnace. Very expensive. If you can use preheat, if it is a low preheat, you preheat it with a torch, like you were saying. If the preheat is too much, then it gets expensive again. And like everything in welding, there's no universal solution, because maybe you already had like heating blankets already in your shop, and doing a preheat is easy. Maybe you already have a heat treatment furnace and small parts, right? But what really matters is not that there is a universal solution, it's that there are many possible solutions, and you're aware of those, and you know why you would need them. All right, another thing that is important, I mentioned this like briefly, but this CCT diagram is for a given prior austenite grain size. We're going to see that different grain sizes of austenite give you different results. It's not radically different, but it's different enough to know that this thing is not perfect, right? So CCTs are not perfect for welding. We're going to teach you formulas that account for this austenite grain size, right? So by the way, I understand you have the CME people have a DBR lecture this Thursday, right? Is that true or not? The graduates in MADI. Is it true? Yes. Okay. Okay. So we didn't send you a note, but we are going to have the seminar today. Is that okay? You can have the seminar today? If you get a sandwich? Say?
Hopefully not today.
Have
an exam later.
Oh, God. Okay. Well, we'll figure it out. We're going to have it. It's not going to be on Thursday. So we'll figure out what happens, because, but you're in CME. So this Thursday, you'll have to be at the DBR. Okay. We'll figure it out, right? But I want you to learn these formulas to calculate these things, and cannot be on Thursday. And I should have sent you a note, but I didn't. Anyway, so some issues of nucleation. When we nucleate the things that are going to transform, having transformation sites is going to help. For example, if we have large austenite grain sizes, the surface to volume ratio is relatively slow, and because the transformation starts typically in the grain boundaries, so you increase the hardenability by having big austenite grain sizes, right? So the exact same steel, if you overheat it for whatever reason and it's up with huge austenite grain sizes, it's going to be a lot more hardenable than the parts with small grain size, austenite grains. The other thing is inclusions. Some inclusions, like titanium oxides, in tiny amounts, right? They act as nucleation sites, right? And sometimes you nucleate things and they're beneficial. To give you an idea, this titanium oxide is an essential component of welding consumables to get what is called a acicular ferrite. That is a very convenient microstructure. So here we have this schematic. And in this schematic, it tells you how the microstructure is going to evolve in three cases. And this would be low alloying additions, high alloying additions. Which one should be more hardenable? These ones at the bottom or these ones at the top? The ones at the bottom are more hardenable because have more alloying additions, right? Austenite grain size, bigger austenite grain size. The austenite grain size is almost like an alloying element, right? More grain size, more hardenability. Here we have the T85, which you already heard about, right? Like the time to cool from 800 degrees to 500 degrees, right? So essentially this is long times to cool or fast cooling rates. And here's oxygen content. Funny, right? Who cares about oxygen? But the oxygen is tied in the inclusions. So if you have no oxygen at all, you would not have inclusions and you would not be nucleating some components. So let's look at this. You see this hexagon is the common way in which people represent the austenite grain size. And this thing here, this is the primary ferrite nucleating on the grain boundaries of the prior austenite grain size, the prior austenite grain, right? And you see this thing here, this is called Whitman-Staten ferrite, but let's not worry too much about it. But let's be aware, this starts to be into those things that appear as bainite in the CCTs, right? And they grow like fingers into the grain. And this little thing here, these are called acicular ferrite. They are typically good to have, right? So now, if we have more alloying additions, what it says here is you'd have fewer ferrite nucleating at the grain boundaries, right? Less, right? And less of this Whitman-Staten ferrite, but you're going to have more of this acicular ferrite inside. Acicular ferrite grows in a basket weave type of microstructure, so it gives you lots of toughness. It's very desirable. So welding consumables tend to have titanium, not a lot, a little bit. So the titanium, when it's oxidized, generates these nucleation sites for the acicular ferrite. And if we have lots of alloying elements, or we cool down very fast, or we have huge austenite grains, here it says no primary ferrite, right? Do you remember that some of the diagrams said no primary ferrite? And here it says, well, maybe a little bit of primary ferrite. And then we go straight into these bainitic type of transformations, whether it's ferrite with second phase aligned, or they have all these funny names, right? We have this transformation here. So you see three quite different final microstructures of the weld. This tends to be the best. This tends to be okay. This tends to be quite low toughness. So I have a few minutes. I want to try to go quickly over linking the microstructure to the thermal history in the heat-affected zone. You know, this is a CCT diagram now. And I actually have two CCT diagrams superimposed. One is for 1,000 degrees, and one is for 1,400 degrees, right? The one shaded is for large austenite grains, right? As if I held the austenite at 1,400 degrees. The 1,000 degrees is for smaller austenite grains. right? Depends on what your temperature is. In welding, you're going to have different prior austenite grain sizes, right? And here we have what you already saw. Here is the primary ferrite. Here, primary ferrite. Here we have perlite, or for this other austenite grain size ferrite. And here we have the bainite, right? And here we have the martensite. So I'm going to be using the one in dashed line. Someday we're going to generate our own diagrams. Will be a lot better, but now I'm using things I found in the literature. So if my cooling rate in welding is very slow, if my cooling rate is very slow, I'm going to have primary ferrite at the grain boundary, like all this primary ferrite here. Perlite is all these black things here, is a perlite. And then tiny amount of bainite that here appears as ferrite and carbides. Right? And now if I cool down faster, instead of this curve, I have something that is faster. Now I have no more perlite. Right? If I cool faster, I see no more perlite. And you see there's no more black dots here. You see all these black splotches here? That's perlite. No more of those. And we have primary ferrite, and you see all these features. FSA means ferrite with second phase aligned. This is primary ferrite intergranular. These features, they have this bainitic type of character, right? In which we have a combination of displacive and diffusive transformations. If I cool down even faster, I get finer microstructures. Faster, even finer microstructures, right? And you get to see how it's the same thing, right? This white is the primary ferrite, the ferrite and the primary, and these other things are like these bainitic type of structures. And then at one point I'm clipping just a tiny bit of bainite and martensite. You see that the microstructure changed a lot, right? And we have a tiny bit of FSA that is ferrite with second phase aligned. And if we move the cool way too fast, it's all martensite, right? Of course, this would be very brittle and would need to be tempered. So this is how we would be, the effect of cooling rate would be affecting our microstructure. There's an interesting thing that I want to say that I didn't say clearly in the slides. In welding, all the part of the bead and the heat affected zone cools down more or less at the same rate. But you still have a whole zoo of microstructures. The reason is because different parts of the heat affected zone have different peak temperatures. But the cooling rate is more or less the same. What I just showed you is the effect of different cooling rates. And that relates to welding with submerged arc welding, that is very slow cooling rate, or electroslag, or laser welding, very fast cooling rate. But a laser weld, pretty much all places in the weld have the same cooling rate. In a subarc welding, pretty much all places in the weld have the same cooling rate. Okay? So the effect of cooling rate is more related to the process than to the internal metallurgy. All right, couple more things. There is this concept of carbon equivalent you might have heard, right? And there are lots of ways of calculating carbon equivalent. But carbon equivalent gives us a sense of hardenability. So you're going to hear that people don't want to weld steels with more than 0.4 carbon equivalent. That's a pretty good rule of thumb. But I want to do something better with you. And I have asked Alejandro, who's doing his PhD with us on metallurgy, and when he took this class for his final project, he did a compilation of formulas to calculate the hardness that you would expect in a weld. And he will teach those to you today. For those who have to leave, and I'm sorry that I'll make up to you somehow, right? You need to leave, but I want you to learn this. So somehow, and if anybody else needs to leave, my bad. I should have told you in advance. But I want you to learn to use formulas to relate carbon equivalent to cooling rate to hardness. Right? These formulas essentially synthesize what all these things I've been trying to explain to you from fundamentals. I'm going to skip over this because we're going to show you how these formulas go. Look at these formulas, yikes. But you can predict things. Other effects of temperature that affect welding. One is coarsening of the austenite. For example, in electroslag, it's a process that is very hot for a long time. So it gives time for the austenite grains to coarsen very much, right? That means they are very hardenable. That's one thing. The other thing that might affect you is you can prevent the coarsening of austenite when you do microalloyed steels by having things like niobium carbides or vanadium carbonitrides that they're called, they pin the austenite grain size. So welding normal steel can end up in big coarsening, but welding other type of steels might not coarsen so much, right? And this is and this is because of these carbides pin it. However, if it gets too hot, things like the niobium carbides, eventually they dissolve, and the austenite can grow out of control, right? Okay. So other effects of temperature, the dissolution of carbides I just mentioned. In the case of aluminum, aluminum gets its strength mostly from precipitates. And what happens with the welding of aluminum is that the high temperatures of welding dissolve those precipitates. So funny enough, while welding steel often results in carbon steel ends up being too hard in the heat-affected zone, aluminum ends up being too soft in the heat-affected zone because we dissolve the precipitates that made it strong. Right? The converse can also happen. For example, if I'm welding stainless steel and I'm doing it with too much heat input, I can give time for the carbon and the chromium to combine into a chromium carbide. So now the steel is not any longer stainless, and the toughness is horrible. That is called sensitization, right? These are effects of time on all these things. So let's skip this. Something interesting during heating, right? We were talking about cooling diagrams, but during heating, right, I also need to transform. And if I'm heating too fast, for example, in laser welding, the transformation to austenite might take too long, right? And the temperature increases quite a bit for transformation. So I think I don't need to go over this summary. I'm going to stop here. Some of you need to leave. You can leave. If some of you would like to stay, I want to share with you some formulas for calculating hardness. I hope many of you can stay, and then we'll figure out how to do with those who couldn't. Right? We'll make up for it at some other time. Let's stop the lecture here then.